In today's topic, we are going to see similar matrices. Let A be our given matrix A. Matrix A is said to be similar to matrix B if there exists a non-singular matrix P such that B can be written in terms of P inverse A P. Okay. So we have matrix A. Then from matrix A we find out matrix P. Now the procedure of finding matrix P will be described in a next problem session. Suppose we have matrix A. From matrix A we find out matrix P. Then we find out matrix P inverse. Then P inverse A P. This matrix calculation gives us matrix, new matrix. Say this matrix is B. Now we can say that A is similar to B. Okay. Or if both matrices are same, then there must exist some matrix P where B can be written in terms of A as B is equal to P inverse AP. Now note that similar matrix A and B have same eigenvalues. If matrix A and matrix B are same or similar matrices, then both have same eigenvalues. If x is an eigenvector of A, then y equal to P inverse x is an eigenvector of matrix B. These are two invariant eigenvalues properties. First, we will see proof of first. Our first thing is similar matrix A and B have same eigenvalues. Let us see the proof. Given that B is similar to A, from definition we can say that B can be written as P inverse AP. Say this is an equation star. Okay. Now we have to show that eigenvalues of B and A are same. Now eigenvalues comes from roots of characteristic polynomial. So first we will find out characteristic polynomial of A and B. Now let us say CB of lambda, that is characteristic polynomial of B. By definition we can say that characteristic polynomial of B is nothing but determinant of B minus lambda I. If here is any another notation, suppose P, then we will use the same notation here, P. Okay. Now as B is similar to A, this is a given thing, so we can replace value of B by P inverse AP. So instead of B, I write down here P inverse AP. Lambda I remains as it is. Now there is change in I. We can say, we know that I is nothing but P inverse P. I is nothing but P inverse P. Okay. So instead of I write down here P inverse P. Now lambda is a scalar value and P is a matrix. So we know that lambda into P is nothing but P into lambda. This is not true for matrix. For matrix AB is not equal to PA. For matrix AB is not equal to BA, but we know that if there is some scalar value, suppose 2 is multiplied to some matrix 1, 2, 3, 4, this is same as 1, 2, 3, 4 is multiplied by 2. Okay, so here lambda into P inverse, lambda P inverse is replaced by P inverse into lambda. Now here P inverse AP minus P inverse lambda P. Now I take out P inverse common from left hand side. These are two terms. In these two terms I drop out P inverse from left side. So here is P inverse. I carry a P common from right side. So there is a P. So here I get A minus, here remaining term is A, here remaining term is lambda. So I here write down A minus lambda I. Now this is a matrix. Lambda is a scalar value. So I need here matrix. So I write down here I. Due to I, lambda into I become a matrix. Subtraction of matrix and scalar value is not possible. Look, 1, 2, 3, 4 is a matrix, and suppose there is some value 2. Now this subtraction is not possible. So to become this subtraction possible, what we do? We multiply this 2 by identity matrix 1, 0, 0, 1. Now this subtraction is possible. So that I write down here lambda I. Now as we know, determinant of AB is nothing but determinant A into determinant B. So here are three matrices: P inverse, A minus lambda I is one matrix and P is another matrix. So I get it here: determinant of P inverse, determinant of A minus lambda I, and determinant of P. Now as determinant of any matrix is some scalar value, so I can take any value to anywhere. So this determinant of P and this determinant of P inverse, I take it here common, so I get determinant of P inverse into determinant of P into determinant of A minus lambda I. Now determinant of P inverse and determinant of P is nothing but determinant of P inverse P. I use same property here: determinant of A into determinant of B, determinant of A into determinant of B is nothing but determinant of AB. Yes, same here. Now as determinant of P inverse P, but P inverse P is identity matrix, so this is determinant of I. Now as I know determinant of I, that is determinant of identity matrix is 1, so I get it here determinant of A minus lambda I, but determinant of A minus lambda is same as characteristic polynomial of lambda. So thus both matrices A and B have the same characteristic equation, so both have the same eigenvalues, therefore similar matrices have same eigenvalues. Now second, what is given? Given thing is, let x be an eigenvector of A. Let x be an eigenvector of A. Now we have to show that P inverse x is an eigenvector of B with respect to eigenvalue lambda. That means we have to show that what will be our claim. So I write down, so this is given, x is an eigenvector of A, so I have Ax equal to lambda x. Now I have to show that for similar matrix B eigenvector is P inverse x, eigenvector is P inverse x, eigenvalue is lambda, eigenvector is P inverse x. Now here look, this is matrix, this is matrix, this is eigenvector of x, this is eigenvector of A, and this is eigenvector of B. This is eigenvalue of A, this is eigenvalue of B, this is eigenvector here xx, similarly here P inverse x, P inverse. This is my claim. I have to show this. Okay. Now here you can see in this term the same thing is here. Okay, now let us start. As given both matrices are similar, so I have B equal to P inverse AP. Now as I have B equal to P inverse AP, I will look at the claim B is multiplied by P inverse. Look at here, B is multiplied by P inverse. So I multiply P inverse by right side to this equation. So I will get B into P inverse is equal to P inverse AP into P inverse. I multiplied this equation by P inverse from right side, so I will get B equal to B into P inverse and P inverse AP into P inverse. Now here P into P inverse, their multiplication becomes identity, and identity into P inverse A is again P inverse A. Okay. Sorry. Now I have here B, I have here P inverse, so again I multiplied this equation by x from right side, so I will get B P inverse into x is equal to P inverse into A into x. Now here I just change the brackets, B into P inverse into x is nothing but B into P inverse of x, and here Also I change the bracket. P inverse A, this is matrix 1 and second matrix is X. Now instead of this I write down here P inverse is one matrix and A into X is another matrix. But I know that AX is lambda is because for a given matrix A, X is an eigenvector with respect to eigenvalue lambda. So I replace AX as lambda X. So here I get P inverse into lambda into X. Now here as a lambda is in some scalar value, I can take it common from this and I put out here. So lambda into P inverse of X. Now look at the claim. My claim is same here. So let P inverse X is Y. So I have B into Y equal to lambda into Y. This is the same notation as AX equal to lambda X. Instead of X, there is only Y. Both matrices are similar. They have same eigenvalue but need not have same eigenvector. For matrix A, eigenvector is X. For matrix B, eigenvector is Y. They may be same but need not be same every time. Okay. So here Y is an eigenvector of B corresponding to eigenvalue lambda, but Y is nothing but P inverse X. So P inverse X is an eigenvector of matrix B corresponding to eigenvalue lambda. Now note, if matrix A and B have same eigenvalues, if matrix A and B have the same eigenvalues, does not imply that they are similar matrices. What we learn firstly, if matrices are similar, then both matrices A and B have same eigenvalue. But if there are two matrices A, B, both have the same eigenvalue, suppose lambda 1, lambda 2 are the same eigenvalues, but it need not say the matrices are similar. As we all know, P implies Q does not imply that Q implies P. Yes, P implies Q is true, but Q implies P need not be true. So this is the same. For example, now there is one counter example. A is 1 1 0 1, B is 1 0 0 1. Here both have same characteristic polynomial lambda minus 1 square. So here eigenvalue is 1 1, but they are not similar matrices. Okay. Now why they are not similar matrices? Okay, so this will be seen in our next topic. Now we will see some problems regarding this similar matrix topic. How to find out P. This is very important. This is solved problem session. If B is similar to A, we have B equal to P inverse AP. We have B equal to P inverse AP. Now see some examples. Let A is 4 1 2 3. Let B is 2 0 0 5. Are B is similar to A. Okay, we can't say by just seeing at some matrices, we can't say that both matrices are same or not. So every time we need some relations, or we will use definition. Okay, now if I am able to find out some matrix P, okay, then I will find out P inverse. Then already I have A, so by multiplication of P inverse AP, if this matrix is same as given matrix B, then and then only I will say that both matrices A and B are similar. Now the main problem is this: how to find this matrix P. Okay, now we will proceed to find out P. Now given matrix A, we will find out characteristic polynomial. Characteristic polynomial is lambda square minus 7 lambda plus 10. You have to do this on your own. Now by equating this characteristic polynomial with 0, I will get lambda equal to 2 and 5. These 2 and 5 are distinct eigenvalues of A. Now for each lambda, for each eigenvalue, we will find out eigenvector. Now in previous topic, we have seen how to find eigenvector. Okay, you have to check this, means you have to find out list by step. For lambda 1 equal to 2, eigenvector is 1 minus 2. For lambda 1 equal to 2, eigenvector is 1 minus 2. Check this. For lambda 2 equal to 5, eigenvector is 1 1. For lambda 2 equal to 5, eigenvector is 1 1. Okay. Now we required non-singular matrix, which is P. Now this matrix P is nothing but V1, V2. Now V1, V2 are our eigenvectors. Here, this is V1, look, this is V1 1 minus 2, and this is V2 1 1. Okay. Now by this method we will have a matrix P. How we find out matrix P? For given matrix A, we find out eigenvalues. From eigenvalues we find out eigenvectors. Now I put out these eigenvectors in column so that I will get this matrix P. Now you can check that determinant of this P is non-zero. We always require a non-singular matrix P because we have to find out P inverse. Okay. Now this is the matrix P. Now P inverse is nothing but 1 by 3, 1 minus 1, 2, 1. You can check this by using our formula P inverse equal to 1 upon determinant of P adjoint of P. Now let us do our procedure. If I am saying again, if P inverse AP is B, that is our given matrix B will become, then I will say that A and B are similar matrices. Now this is our P inverse that we will find out. This is matrix A and this is matrix P. If I do the multiplication of all these three matrices, I will get this matrix B. We will check that is it B or not. Yes, B is 2 0, B is 2 0 0 5. So I am getting this again same matrix B equal to 2 0 0 5. Now while doing this multiplication of these three matrices, you need to do matrix multiplication of two matrices, any two matrices, no problem. First you will do matrix multiplication of these two matrices. By multiplication of these two matrices you will get one matrix. Then there is this product one matrix and this product this matrix. Take matrix multiplication of these two matrices and then use this coefficient 1 by 3. Okay, there you will get 2 0 0 5. Now here we have P inverse equal to B, that is B is similar to A. Here also you can note that A and B both have same eigenvalues. As we have find out, eigenvalues of A are 2 and 5. Eigenvalues of B, where B is a diagonal matrix, so diagonal matrix, for a diagonal matrix, eigenvalues are nothing but its diagonal elements. So here also eigenvalues of B are 2 5, that is similar matrices have same eigenvalues. Yes. So this is a procedure of finding matrix P. If there is a problem that we'll check whether the matrices are similar or not, then you have to find out eigenvalue of A, eigenvectors of A, and from that eigenvectors you have to prepare one non-singular matrix P, and matrix multiplication P inverse AP will give you B. If this matrix B is same as your given matrix, then you are through. You can say that B is similar to A. Okay, thank you.